So the second part of this lesson is integrating exponential functions. So just like we did with the log functions, we're going to use a lot of integration by substitution. Kind of the key idea is that the derivative of e to the x is e to the x. So the integral of e to the x is just e to the x. And again, if I have an indefinite integral, I have to make sure I put my plus c. Now, if this x in the exponent is anything other than an x, you may have to think of using integration by substitution as long as it works. So let's try the first example. If I look at the exponent, the derivative of the exponent is 3, and I'm missing just a number, which is fine because I can introduce the number on top and bottom. So I'm going to let u equal 3x plus 1. My derivative with respect to x is 3, and I multiply both sides by my dx. So du becomes 3 dx, and u becomes 3 to the x plus 1, so my integral becomes 1/3. That 1/3 can be on the inside or outside, e to the u du, and then based on this little theorem here, the integral of e to the u is just e to the u. So this is 1/3 e to the u plus our arbitrary constant. And then I sub back my u with x's, e to the 3x plus 1 plus c. Okay, same idea here. My inner part of the function is kind of like the exponent. The derivative of the exponent, or the something, is minus 2x. There's a 5x there. So what I'm going to do is I'm going to introduce a minus 2 and a minus 2. And then I'm going to do integration by substitution. So u is equal to minus x squared. My derivative is minus 2x dx, and I multiply that x onto the other side. So my u becomes the exponent. My minus 2x dx becomes my du step, and everything else not highlighted is just a constant. So I'm going to bring all the numbers out front. 5 over minus 2. E to the u du, and then I'm ready to go ahead and integrate. So the integral of e to the u is e to the u, and then because it's an indefinite integral, I need my plus c, and then I just sub back in my u, which was minus x squared plus c. Again, most of these examples are quite similar as what we've always been doing. You just have to recognize what is sort of that inner function or the composition part of the function. So here I kind of see two functions. I see e to the something and then divide by x squared. So the something part in the exponent is kind of like my substitution step if it's going to work. So if I let u equal 1 over x, which is also x to the minus 1, my derivative is minus 1x to the minus 2, and then I multiply both sides by dx. So you can see here du is minus 1 over x squared dx. I'm only missing the negative sign, so I'm going to introduce it on top and bottom. So now my integral becomes minus 1 integral. Now you'll notice that this x to the minus 2 sits on the denominator, which is where we want it to sit. So minus 1 over x squared dx becomes du, and my integral becomes e to the u du with that extra negative 1 floating on the outside. The integral becomes the same thing, plus my arbitrary constant, and then I sub my u back in. For part B, hopefully you can see it's kind of obvious what your substitution will be. There's a sine x on the outside, but the e and the cos are kind of mixed together, so there's a composition happening. I let u equal the exponent, which is cosine x. My derivative sits on the base, which is minus sine x dx. I'm missing a minus 1, so I'm going to introduce the minus 1 on top and bottom. Minus 1 sine x dx becomes my du, and my cos x becomes my u. So again, most of these integrals are just turning into our e to the u du because of the derivative sitting kind of in that integral step. The integral of minus 1 e to the u is just minus e to the u plus c. I sub my u back in, which is cosine x, plus my c. And that's the answer. And again, you can always check your answer because you're going to take the derivative of the answer to check. And if you get the original function, you know you've done the derivative or the integral correctly. Now again, part of I4 is finding areas under curves, but this finding areas also intersects with our outcome I1 and I2 because of the areas under curves. So the area under the curve represents the integral. Now again, this is referring to the area under the curve between 0 and 1 for the e to the minus x function. So if I were to draw e to the minus x, that's my exponential decay function. From 0 to 1, let's just say 0 to 1 is right there. So there's 0, there's 1. It represents this area under the curve. And this function is y equals e to the minus x. So again, here, my u would be minus x. The derivative would be minus 1 dx. I'm missing the minus 1, so I introduce it. When x is equal to 0, u is equal to minus 0, which is 0. When x is equal to 1, u is equal to minus 1, which is minus 1. Now you can't worry about where the numbers show up if one is bigger than another. You just have to put them in kind of where you get them. So you'll see what I mean by that. Minus 1 dx is my du. So the integral becomes when x was 0, y was 0, u was 0. When x was 1, u was minus 1. So even though that number seems awkward that way, you still need to write it in that same order. And then my integral becomes e to the u du. And then that integral just becomes minus e to the u. We don't need our plus c because we have a definite integral. And now I just sub in my value. So so this would be negative e to the minus 1 minus negative e to the 0. And e to the 0 is 1. So this is minus 1 over e. E to the 0 is 1. And then minus and a minus make plus. So that represents the area under that curve or that little section I've marked down for you there. Same idea for all of these questions. They're all integration by substitution. You just have to recognize the substitution. So we'll pull this one on the side here. Let u equal 1 plus e to the x. My derivative is equal to e to the x dx. You can notice that e to the x dx is on the numerator where I need it. 1 plus e to the x sits on the denominator. And then when x is equal to 0, u is equal to 1 plus e to the 0, which is 1 plus 1, which is 2. When x is equal to 1, u is equal to 1 plus e to the 1, which is just 1 plus e to the 1. So now my integral becomes 2 1 plus e to the 1 goes on the top. 1 du divided by u. And then you have to think this related to the last lesson we did, ln of absolute value of u from 2 to 1 plus e to the 1. And then we just sub that in. Ln of 1 plus e minus ln of 2. And then that would be my final answer, and I'm happy if you leave it like that. I'm going to kind of box this in before I do the last example so it doesn't kind of cut in. Maybe I'll just kind of put a little line there. And we can start working on that second example, and I'll do it in another color so in case it kind of comes close by, you'll know that it's a different example. So for part C, we're going to let u equal e to the x, which is coming from this inner part here. The derivative becomes e to the x dx, kind of sitting on the outer part of that function. So there's my u. Whoops, not there. There. That's the one I intended. And then my e to the x dx becomes my du step. If x is equal to minus 1, u is equal to e to the minus 1. If x is equal to 0, u is equal to e to the 0, which is 1. So my integral becomes e to the minus 1 to 1 cosine u du. What is the integral of cosine of u? Is sine u, because the derivative of sine is cosine. Now again, when we're doing this, it's not necessary for us to put our x's back in because I changed my limits of integration to u limits. So I'm just going to come down here. So this will be sine of 1 minus sine of e to the minus 1, which is the same thing as 1 over e. And I'm going to leave my final answer in this format. And that's, again, integration by substitution with some of the exponential and log examples. You'll notice there's a whole schwack of problems down here for you to try. If you run into any troubles, feel free to send me an email and we can talk about them. And that's that.